Hello, welcome to the Preparatory workshop for the Foundations courses. So this video will be on the axioms of Zermelo-Fraenkel set theory. So Zermelo-Fraenkel set theory was developed in the early 20th century as a formal theory of sets which was meant to be free of the paradoxes that appeared in Russell's approach to naive set theory. So this was developed by Ernst Zermelo and Abraham Fraenkel, and it is based simply on sets and membership between sets, and everything is expressed in first-order logic, and it's expressed in terms of membership. So the axioms are the following. First of all, we have the axiom of extensionality. This says that if two sets x and y have the same elements, then x is equal to y. Secondly, the axiom of pairing says that for any sets A and B, there exists a set which contains exactly these two sets A and B. Thirdly, the axiom schema of separation. So it's a scheme because there's an axiom for each property, P, with parameters. So if P is a property, which is defined by parameters, then for any set and for any choice of parameters, there exists a set Y that contains precisely all those elements of X that have the property P. Next, the axiom of union says that for any set X, there exists a set Y, which is the union of all elements of X. The axiom of power set says that for any set X, there exists a set Y, which is the set of all subsets of X. Next, the axiom of infinity says that there exists an infinite set. The axiom scheme of replacement, and again, this is a scheme because we get one for every class function, and I'll explain what all of these things are in a bit. So if f is a class function, then for any x, there exists a set y containing precisely the image of x under this class function. And finally, the axiom of regularity, otherwise known as foundation, axiom of foundation, says that every non-empty set has an epsilon minimum element. Okay, so before I explain everything formally, let me first of all explain some notation issues. So as I was saying a few moments ago, everything in set theory is expressed in first-order logic in an appropriate language. And this language consists of a single binary relation symbol, epsilon, which denotes membership. So everything, and when I say everything is expressed, I mean everything. It is expressed in terms of this. And it is very often that for predictability purposes, we use shorthand notation. For instance, the notation, well, x is a subset of y, is simply shorthand for all sets z. If z is a member of x, then z is a member of y. Okay, more shorthand notation. If phi is a formula in the language of set theory, then the notation for all x in y, phi, simply says that for all x, if x is in y, then phi, while the notation there exists an x in y such that phi says that there exists an x such that x is in y and phi. Okay, by a class, we simply mean a formula in the language of set theory that has a single free variable. So for instance, the formula x equals x denotes the class of all sets. Why? Because everything satisfies this formula. And for a class, the notation, say a class C, the notation x is in C, technically C is not something that we can talk about. So technically the notation epsilon would not sort of apply to it. But x equals C is simply shorthand for C holds of x. The notation right here denotes the set whose elements are precisely x1 up to xn. So for instance, if in a formula one wanted to say that the set x1 up to xn containing x1 up to xn is in S, this would simply be shorthand for there exists a set such that all elements of it are precisely either x1 or x2 or and so on up to xn, and this set is in S. Okay, the pair now, xy, This is called an order pair. And for order pairs, we use what is known as the Kuratowski encoding, which is simply the following. So the order pair xy denotes the set containing x and the set containing xy. Okay, now that I've settled this, hopefully some of the axioms I mentioned before start to make more sense. And so these being axioms, they should be formally expressible in the language of set theory. And so what I would like for you to do now is to pause this video and try to write for yourselves each one of these using a proper formula, first-order formula in the language of set theory. So please pause the video and try to do that. Okay, so assuming you've had a go, let's see how we can formally express these axioms. So extensionality. Extensionality once again says that if two sets x and y have the same elements, then they are equal. How can we say this? Well, for all sets set x and for all sets y, if it holds that for all z is in x, if and only if z is in y, then x is equal to y. Okay, so this is simply a sentence in the language of set theory. It only uses the epsilon binary relation symbol and just quantification and Boolean connectors. Pairing. So pairing, recall that it should say that for any two sets, there's a set that contains exactly these two things. How can we say that? Well, it should say for all x, for all y, so these are the two sets, there exists a set, z. Now what I want to say is that all elements of it are precisely x and y. So that's what I'm going to say. So for all w, these are going to be elements, w is in the set z if and only if w is equal to x or w is equal to y. This is pairing axiom. Separation. Now separation, recall I said before that it's an axiom scheme, so we get one axiom for every property, and these are properties that could possibly have parameters. Okay, and what separation says is that for any set x and for any choice of parameters, there is a set containing exactly those elements from x that have this property. How do we say that formally? Well, for all possible parameters that we could plug into this formula, and for all sets x, there is a set y. Now what I want to say is that the elements of y are precisely those elements of x that satisfy this formula, and that's exactly what I'm going to say. So for all z, z is in y if and only if z is in x, and phi halls of z, p1 going out to pn. Good. Union, recall that union says the following informally. For any set x, there's a set y, which is the union of all elements of x. Okay, how can I say this formally? Well, for all x, there exists a y, such that for all z, z is an element of y, if and only if, for all w, w is in x implies that z is in w. Why is that? I want to say, so recall what I'm trying to say is that y is the union of x. So it should be that all the things that are in y are precisely members of x. And that's what I've written above says. Okay, power set. So what the power set axiom says once again is that for any set x, there's a set y which contains the set of all subsets of x. Okay, hopefully you're starting to get the sort of idea behind these. So power set formally will say the following. For all x, there's a set y such that I want to say the members of y are precisely the subsets of x, and that's what I'm going to do. So for all z, z is in y if and only if z is a subset of x. And recall z is a subset of x is shorthand, again, notation for all members of z are also members of x. Okay, infinity might have been a bit tricky, well, because in the way that I phrased it before, it's very vague. So it says that there exists an infinite set, but what does this even mean? How can you even describe this using just the epsilon relation? So what we want to say is that there exists a set that has infinitely many things that are different. So in order for them to be different, it must be that their elements are different. So they differ by something, say, is in one, but it's not in the other. And that holds for each pair of such things in this set X. So the usual way of stating infinity is as follows. So what it is going to say is that there exists an X, first of all. Okay, this is going to be an infinite set, such that the following. So first of all, I start from something, and I start from some set Y, which I claim to exist, which is the empty set. Okay, what does it mean to be the empty set? This is again shorthand notation for the formula that says that there's nothing in Y. Okay, so I've got this set Y that I know that has nothing in it, and I also require that Y is an X. Okay, so I've put one thing in my X. I want my X now to be infinite. How can I say that my X is infinite? Well, I'm going to say the following. I'm going to say that for all things, for all W, if W is in X, then W plus is in X. And what do I mean by W plus? I want to somehow create a new set from W that is different from W itself, so as to sort of get infinitely many things in X. And I know that I've got at least one, so if I keep plussing stuff, I'll get infinitely many things. So what is this plus, and how can I make sure to that this is different? So this plus, first of all, it denotes the following set. So W plus is simply the set, as I've written here, W union the singleton W. Okay, it is clear that W plus is not equal to W. Why is that? Because W plus contains W itself, but W does not contain W. Okay, and why does it not contain W? Well, it follows from foundation, but we will see that in a bit. Okay. So how do I say that W plus is next? What I can say simply is that there is some set such that this set is equal to W union the singleton W, and this set is next. Okay, and then I simply need to say again what it means to be equal to W union the singleton W, and what this means is that all elements, so for all things S, for all S is in T if and only if S is in W or S is equal to W itself. Okay, so let me describe once again the intuition behind this. What I say is that there exists this set such that the empty set is there, and I can describe the empty set. I simply say that it's this set that has nothing in it. And then what I say is that for everything that is in my set X, I can always get this W plus to be in my set. Okay, and I can make sure that this W plus is always different from W, and in fact, it'll be the case that W plus is a proper superset of W, and so we get a chain, a strict chain of these sets, okay, and therefore they're all pairwise different, and so it's strict increasing chain, and I therefore have my infinite set. Okay, to be more precise, this says that there exists an inductive set, but okay, I won't dive more into this. Replacement, recall that this is once again a scheme, so I get one axiom for each class function. Now, what does it mean to be a class function? This I also did not explain. But it's a lot like a class, and it's a lot like a function. So it's a lot like a class in the sense that it is a formula with two free variables. And it is a lot like a function in the sense that it satisfies that for all things in the first coordinate, there exists a unique thing in the second coordinate, such that this formula holds of the pair. Okay? So let's first of all say that, because the axiom starts by saying if f is a class function, okay, so how do we express this? What we need to say is what I told you before. So for all s, there exists a t, okay, and first of all I say that of st holds. Okay, so s is sort of the input, t is the output. But I want this to be unique in order for this to be a function. So it should be that for all p, if fsp holds, then t is equal to p. So there's a unique kind of t for which this holds. Okay, and this describes that f is a class function. Right, so assuming that f is my class function, now I want to form the image of any set under f. And how do we do that? We say that for all x, there exists a set. I want to say that this is its image under f. How do I do that? I say that for all things z, for all z, z is in y, if and only if there is something in x such that phi some w, such that phi of wz holds. And this precisely implies that y is going to be the image of x under f. Okay. Finally, the axiom of regularity or foundation says that every non-empty set has an epsilon minimal element. Okay. So epsilon minimal, it's going to be minimal in the sense that I'll describe now. So it should say that for all sets x, there exists some y, which is in x, so this is going to be the minimal thing. How do I say that it's minimal? I simply say that there's nothing else in x, so there's no z, such that z is in x, and z is in y. So I can't find anything within x such that z is contained in y. Y is the minimal epsilon, the minimal element in x with respect to the epsilon relation. Okay. And finally, I can therefore define ZF as the following set of axioms. It's going to contain extensionality. So formally, it's a set of axioms containing extensionality, pairing, union, power set, affinity, foundation. All of the instances of separation, so for all such formulas phi in the language of set theory, and all of the instances of replacement, again, for all such formulas f of xy. And this gives us ZF. Okay, I'll finish with an exercise. So what I'd like you to do is to argue and try to figure it out for yourselves which axioms of the 8 axioms I gave you above are needed to construct the following sets. So first of all, the empty set. Secondly, the set of order pairs coming from 2 sets A and B. So this is denoted as A, okay, as you probably know from a first year mathematics course, as A times B, and it has all the ordered pairs. But what I want you to do is to justify why this always exists as a set, provided that A and B do, and which axioms are needed for this. And finally, I want you to justify and to explain which axioms are needed to construct the set of functions from A to B, where A, B are 2 sets. And what is a function? Well, as I was explaining, everything in this framework, so, and when I say everything, I mean everything, is a set, and therefore a function is also thought of as a set of ordered pairs. Okay, so it's a subset of A times B, and the fact that it represents a function is a lot like what it means for a formula with 2 free variables to be a class function. Meaning that for every for every x that appears in the first coordinate of an ordered pair in F, there exists a single y that appears together with x in the second coordinate as an element of F. So I'd like you to argue this.